Hello everyone. Today we are going to discuss about the chapter Electromagnetic Induction. It is very important for examination point of view. So in this chapter, the first topic is Faraday's experiment. This Faraday's experiment is the converse of Oersted's experiment. In Oersted's experiment, we have discussed that when current passing through a coil or a conductor, it acts like a magnet. That means it produces magnetic field. So according to Oersted's experiment, when there is a change in the current, magnetic field is produced. Now this Faraday's experiment is converse of that Oersted experiment. Converse means reverse of that experiment. So in that Oersted's experiment, when there is a change in the current, magnetic field is produced. But here, when there is a change in the magnetic field, there will be a change in the magnetic flux. When there is a change in the magnetic flux, an induced EMF is developed in the circuit. This induced EMF is called induced electromotive force, and this phenomena is called as electromagnetic induction. That is what this chapter. So in this chapter, we are discussing about Faraday's experiment. That means this Faraday performed many experiments, and using these experiments, he explained two laws. Those are Faraday's laws. Those Faraday's laws are very important for 2 marks in IPA. So in this first experiment, you can say that there is a magnet, and this magnet is having north pole and south pole. And we know that when there is a magnet, around that magnetic field will be there up to a certain extent. And we also know that magnetic field is represented by the magnetic field lines. You can see here, these are magnetic field lines. When this magnet is moving towards this coil, what he observed, that is the first experiment. So in this experiment, you can see this is a coil, and this coil is connected to a galvanometer. If you observe here, there is no battery. It is connected to a galvanometer. Now this coil is at rest position, and a magnet with its north pole facing towards the coil is brought towards the coil. So when this magnet is moving towards the coil, the number of magnetic field lines cutting across the area is changed. That indicates there is a change in the magnetic flux. So when these magnetic field lines, that means when this magnet is brought towards the coil, he observed there is a deflection in the galvanometer. That means this galvanometer pointer has shown some deflection. Then immediately he moved this magnet away from the coil. Then he observed the galvanometer started showing the deflection in the other direction. And his second experiment is this. Okay, this is a coil. This coil C1. This coil is connected to a galvanometer, and there is another coil that is connected to a battery. We know that when battery is connected, current passes through the coil. So current passes through the second coil, coil C2. And we also know that according to Oersted's experiment, when current that is passing through the coil, it acts like a magnet. So now this coil is acting like a magnet. When this coil is brought towards this coil C1, he observed that there is a deflection in the galvanometer. Then he started moving this coil C2 away from coil C1. Then he observed the galvanometer started showing the deflection in the opposite direction. That means in the experiment, he observed the same effect what he observed here. So from these two experiments, he concluded that when there is a change in the magnetic flux, when the magnet is moving towards this coil, there is an increase in the magnetic flux because the number of magnetic field lines cutting across the area increasing. So there is an increase in the magnetic flux. So due to the increase in the magnetic flux, this galvanometer is showing deflection in the sense the current is passing or current is induced in this coil, and the current is induced due to the EMF. And he also observed that this magnet that is moving away from the coil. When the magnet that is moving away from the coil, there will be a decrease in the magnetic flux. When there is a decrease in the magnetic flux, then also he observed that the galvanometer is showing the deflection. That is, induced EMF is produced. Even in that case also, current is induced in this coil. So from this he concluded that whether the magnet is moving towards or away from the coil, there is a change in the flux. Why? Because there is a change in the magnetic flux. So that change in the magnetic flux produces an induced EMF in the coil, and that further produces the current. So this EMF is called as induced electromotive force, and the phenomena is called as electromagnetic induction. So in the previous experiment, we have discussed that magnetic flux. So first of all, what is magnetic flux? In electric field chapter, we have discussed about electric flux. Electric flux means the number of electric field lines. But here it is magnetic flux. Magnetic flux means the number of magnetic field lines cutting through a surface, and that is across the area. So here if you observe, there is a magnetic field. And we know any magnetic field that is represented by magnetic field lines. So all these are magnetic field lines, and these magnetic field lines are generated due to a magnet. So in that, consider there is a small area. Okay, this is area. Now, in order to find out the magnetic flux cutting across the area, divide this entire area into small and equal length elements, and consider one of such area element is ds. Okay, so here why we are cutting this entire area into small and equal area elements? Because it is very difficult to calculate the magnetic flux due to the entire area. So first we will cut this entire area into small area elements, and after finding the magnetic flux due to each and every area element, we can find the summation of that. Or we know summation is replaced by the integration, so we can take the integration. So for that only, first the entire area is divided into small and equal area elements. One of such area element area is, consider it as ds. Small, no, that is why we consider it as ds. Now you can see here a unit vector. Area is not a vector quantity, so we cannot take the angle between area and the magnetic field. That is why draw a normal to this area. So now that normal is making an angle theta with the direction of magnetic field induction. Okay, so the number of magnetic field lines cutting across that small area is given by d phi. Okay, we can also write it as d phi b because it is a small flux due to the small area. So d phi b equals to b dot ds. We know if we remove this dot, we get an angle. Okay, cos of angle. So if I remove this dot, you will get b ds cos theta. The theta is what? It is not the angle between B and S. It is the angle between B and the normal that is drawn to the area. So we know now what is the magnetic flux due to the small area element, that is d phi, which is equals to B dot ds. Now I told you already. Okay, if you know the small flux, that is flux due to the small area element, we can find out the total flux. How we can find out? We can add what is the flux due to each and every element. So instead of adding, the summation can be replaced by the integration. So here I can integrate this equation in order to calculate the magnetic flux over the entire area. So the magnetic flux due to the entire area is obtained by integrating this equation. So integration of d phi equals to integration of b dot ds. Integration of d phi is what? It is phi. So phi equals to integration of b dot ds. I told you already, if we remove this dot, what you will get? Cos theta. So phi equals to integration of B ds cos theta. So this is the expression for magnetic flux. So this amount of magnetic flux depends on this angle. Okay, so if this angle, that is theta, equals to 0, if this normal drawn to this area is, let us say, parallel to the magnetic field. If this normal drawn to the area is parallel to the magnetic field, theta is 0. If theta is 0, we get cos 0. What is cos 0? It is 1. So we get phi is integral of B ds. So we get bs. So when there is no angle, when theta equals to 0, the flux is maximum, which is bs. If theta is 90 degrees, if the normal drawn to this area is like this, if the plane of the area is in such a way that the normal drawn to the area is perpendicular to the direction of the magnetic field, then the magnetic flux is, what I will write, integration of B ds cos 90. Cos 90 is 0. So the flux is 0. So in this way, depending on the direction of the area and the magnetic field, this flux will change. And this flux is a scalar quantity. The unit of magnetic flux is Weber, or it is Tesla meter square. So this is about magnetic flux. So already we have discussed what Faraday he has concluded with his experiments. From both the experiments, he concluded that when there is a change in the magnetic flux, an EMF is induced. That is what Faraday's first law. So according to Faraday's first law, whenever the magnetic flux linked with a circuit is changed, an EMF is induced in the circuit. This is Faraday's first law. So what we are saying here, that we are writing in equation form. That is what Faraday's second law. See what here we are saying, that there is a change in the magnetic flux. Change in the magnetic flux in the sense it can be increase in the magnetic flux or decrease in the magnetic flux. The increase or decrease in the magnetic flux is denoted by d phi by dt in mathematical form. D phi by dt indicates change in the flux with respect to time. And what we are saying here, when there is a change in the flux linked with a circuit, EMF is produced. So the EMF is denoted by E. Okay. So the developed induced EMF is directly proportional to the negative rate of change in the magnetic flux linked with the circuit. That is Faraday's second law. So according to Faraday's second law, E is directly proportional to the negative rate of change of magnetic flux. So what we can write, E is directly proportional to minus d phi by dt. If I remove this proportionality, we know we get a constant. So E equals to minus, because negative rate, so minus constant n into d phi by dt. Actually, this n indicates the number of turns in a coil. We know that when there is a change in the flux in a coil, if the coil is consisting of only one turn, I'll substitute here n is 1, so E equals to minus d phi by dt only you will get. If there are 3 turns, then E is how much? It is directly proportional to minus d phi by dt in each and every coil. The d phi by dt indicates in each and every coil. So if there are 3 turns, we substitute 3 here. So E equals to minus 3 d phi by dt we write. That means here the induced EMF is also depending on the number of turns. We may get a doubt that why we are writing this negative sign. So this negative sign indicates that this EMF always oppose the change in the flux. That is what we discussed in the next topic, which is Lenz law. So before explaining that, we will see how the change in the magnetic flux. So actually this change in the magnetic flux is depending on B, A and theta. And not only on B, A and theta, also the change in the magnetic flux also depending on the change in the shape of the coil in the magnetic field. It is also depending on, I told you already, when there is a change in the magnetic flux linked with a circuit. That means if there is a coil and when the magnet is brought towards this coil, in the first experiment we can see that when the magnet is brought towards the coil, then in the coil there is a current that is produced or EMF that can be generated. So here it is depending on the change in the flux depending on the change in the shape of the coil in the magnetic field. And not only that, it is depending on the terms B, A and theta. So this B and theta, why we are writing, we know that flux phi is B dot A. Area is denoted by S. In the slide we have discussed. Okay, S. But that S is area, so I can also write A. We have already discussed flux phi B is integration of B dot ds. The maximum flux is Bs. If I write B dot ds, it is B ds cos theta. That means it is depending on, flux is depending on B, area and angle theta also. So that is why the change in the flux is depending on magnetic field induction B, area A and the angle between B and A. So I can say if there is a change in the magnetic field induction, there is a change in the flux. Or if there is a change in the area, there is a change in the magnetic flux. If there is a change in the angle between B and A, then also there will be a change in the magnetic flux. So due to this change in the magnetic flux, EMF can be induced. And the next topic is Lenz law. So in this Faraday's experiment, we have already discussed this experiment. In this experiment, you can observe this. See, there is a magnet with its north pole facing towards the coil is brought towards this coil. When it is brought towards this coil, what did he observe? There is a deflection in the galvanometer. And he immediately moved this magnet away from the coil. Then he observed that the galvanometer is showing the deflection in the opposite direction. And in both the cases, there is a change in the magnetic flux. So, EMF is generated in this coil and further it produces current. Okay. But in this equation, if you see, E equals to, we are not simply writing E is equals to d phi by dt. It is equals to minus d phi by dt. This minus indicates, this negative sign indicates the direction of EMF. So what is the direction of that induced EMF? The direction of induced EMF according to Lenz law is, it opposes the original cause that produces it. If you simply read the statement, we can't understand anything. Actually here what they are saying, it opposes the original cause that produces it. So what is it? It is the induced EMF. So what does this induced EMF will do? It produces. Why it is produced? According to Faraday's law, EMF is induced due to change in the magnetic flux. So the cause for the development of this induced EMF is, what is the actual cause? The change in the flux. So it develops due to the change in the flux. So that is the original cause for the development of this induced EMF. So it develops due to that and immediately it opposes that cause. That means it opposes the change in the flux. So for example, there is an increase in the flux. When there is an increase in the flux, according to Faraday's law, what will happen? EMF is induced. Now this developed induced EMF, what does it do? It tries to decrease the flux. As it is increasing, it develops. But after developing, it tries to decrease the flux. Suppose if there is a decrease in the flux, When there is a decrease in the flux also, I can say there is a change in the flux. So EMF is induced. And that developed EMF, what does it do? It opposes the original cause. Actually, what is the original cause? The decrease in the flux. So this EMF tries to increase the flux. So that is observed by this Lenz law. You can see the diagram, and with the diagram also you can understand that. See, in the experiment, we have seen that a magnet that is brought towards the coil with its north pole facing towards the coil. And according to Faraday's law, when the magnet is brought towards the coil, the number of magnetic field lines cutting across the area will change. So there is an increase in the magnetic flux. And you can also observe that this magnet is brought towards the coil. So there is an increase in the flux. Due to the increase in the flux, what will happen? EMF is induced. And that produced EMF further produces the current. So current will develop. So in a coil, when current is developed, we know that it acts like a magnet according to Oersted's experiment. So here EMF is induced, due to that current is produced in that coil, and when current is produced in the coil, it acts like a magnet. So it acts like a magnet with its north pole facing towards this north pole. See, here there is a magnet, and now this coil is acting like a magnet due to the induced EMF, which further produces the current. So now a north pole is generated. So you can see that there is a magnet, north pole facing towards another magnet with its north pole. So when there are two like poles, in the magnetism we have discussed, like poles always repel each other. So this magnet, now this coil, when current is passes through this coil, it tries to oppose this magnet. It will not allow this magnet to move further. That is what is explained by this Lenz. So that is Lenz law. Similarly, here you can see, when the magnet is moving away from the coil. When the magnet is moving away from the coil, we can say the number of magnetic field lines cutting across the coil are decreasing. So there is a decrease in the magnetic flux. When there is a decrease in the magnetic flux, according to Faraday's law, EMF is induced in the coil and it further produces current. We can say current direction is in a clockwise direction. And according to Oersted's experiment, when current that is passing through the coil, it acts like a magnet. So now this coil is serving like a magnet with its south pole facing towards this north pole. So here magnet is moving away, and this is now a magnet with its south pole facing towards this north pole. North and south. So both are unlike poles. And we know unlike poles attract with each other. So this tries to bring this magnet towards. Actually it is moving away. But because of this induced current, it acts like a magnet and a south pole is generated. So it tries to attract it. So this is what Lenz law. So according to Lenz law, what we can say, when the applied flux density in a closed circuit is increased, if there is an increase in the magnetic flux, according to Faraday's law, EMF is induced or current is induced in the closed circuit. And the direction of that EMF is in such a direction that it opposes the flux density. So here there is an increase in the flux. So this EMF tries to decrease the flux, which is the magnetic flux density denoted by B. Suppose when the flux density in a closed circuit is decreased, when there is a decrease in the magnetic flux, due to the decrease in the magnetic flux, EMF is generated and it further produces current, and the direction of that current is in such a way that it opposes the original cause. What is the original cause? The decrease in the flux density. So it opposes means what does it do? It tries to increase the magnetic field induction. Okay. So So we have discussed about this Lenz law. So you understood this. The next topic is motional electromotive force. So what is this motional electromotive force? That is, what is the expression for induced EMF? So in this diagram, we can see that there is a straight conductor. This is a straight conductor that is moving in a uniform and time independent magnetic field. These crosses and all, we can see that those crosses are representing the magnetic field. So inside the magnetic field, a rectangular conductor PQRS is placed. You can see a rectangular conductor here, PQRS of length x and breadth L is placed in the magnetic field. Okay, so this end PQ is movable. It is not fixed in this rectangular conductor. So it can be moved in the magnetic field. So that is what we have taken. So here what I said, there is a rectangular conductor PQRS of length x and breadth L. So the area of this rectangular conductor, what I can say, L into x, because area of the rectangular is length into breadth, so x into L or L into x. And it is placed in the magnetic field. And what is the one more condition, that one end of this rectangular conductor is movable. That means this rectangular conductor PQ is moving in a time independent magnetic field. Okay. So this rod PQ is moved towards left with a constant velocity v. See, when this rod is moving towards left with a constant velocity, I can say for the next instant of time, this conductor will not be here. This one end, one side of this rectangular conductor will not be here. It will come to this position. So we can say that when this conductor is moving towards the left, there will be decrease in the length. So this x will change, because say it is not at fixed position. It is moving towards this. So in the next instant of time, it may come to this position. So now the x is not equals to this value. Now x value will be changing. So there is a change in the x in the sense there will be a change in the area. When there is a change in the area, I can say there is a change in the flux. Why we can say there is a change in the flux? Because we have already discussed here, the change in the flux is depending on V, A and theta. It is also depending on A. So here that is what you can see. There is a change in the area. So when there is a change in the area, the flux linked with the circuit will change. And according to Faraday's law, when there is a change in the flux, EMF is generated. So what is that EMF that is generated? We are going to find out. So first, what is flux? When the rectangular conductor PQ, movable conductor is here, I can say the area is L into X. So what is flux? The maximum flux is B into A. So B into L X. So the flux is B L X. Okay, I told you already. This SR and parallel to that SR is PQ, so both are equals to L, and here you can see PS, and that is equals to RQ, both are equals to X. So area of that rectangle PQRS is L into X, and it is placed in the magnetic field. So the magnetic flux cutting across this area LX is BLX. Now this PQ is moving with a velocity v. So there is a change in the area. This change in the area produces the change in the flux, because area is changing. So there will be a change in the flux. And according to Faraday's law, when there is a change in the flux, an EMF is induced. And what is Faraday's second law? E equals to minus d phi by dt. Here flux is changing. Okay, so EMF is generated. According to Faraday's law, E equals to minus d phi by dt. What is phi here? BLX. That you substitute in this equation. So if I substitute this equation here, what I will get? E equals to minus d by dt of Blx. Okay. So if you observe, this magnetic field induction is constant. Length is not changing. So that is also constant. So I cannot differentiate that with respect to time. So those two are constants with respect to time. So what is changing with respect to time? This x is changing because this one end PQ, we are moving in this direction towards left with a velocity v. So there is a change in the x value. So I can differentiate only that x. So minus dl, we get dx by dt. dx by dt is what? The rate of change of displacement. We know the rate of change of displacement is velocity. So this is v. We get E equals to minus dlv. So the expression for motional EMF is E equals to minus dlv. Here I did not write negative sign because we know negative sign indicates that the direction of EMF. According to Lenz law, the direction of EMF is what? It opposes the original cause that produces it. Here actually E is developed due to motion of this PQ. So this EMF will develop and it opposes this motion of PQ. Okay. As it indicates only direction, the magnitude of EMF is BLV.